So, good afternoon everybody for coming. Who has an announcement about
Just I would like to introduce you, one of the attendants. Just joined the institute, will stay with us at least for 6 months more, and just welcome. The office is 106.
102.
Yes, well, yes, there is a short visit as Alberto Valderá, which will be here all the week, and with Francesco Dovidio was around, but I don't see him. But they will be here for this week. They're coming from France, from Paris, working on some ocean diagrams.
So, it is a great pleasure to introduce the first talk by Konstantin Klemm as the Monica Hart Fellow at our institute. So, welcome Konstantin. So, probably most of you already met Konstantin in the past, but just to a short overview of what he has been before. So, he did a PhD in Copenhagen at the Niels Bohr Institute. Then he moved to Leipzig for several years in several centers, but all related with bioinformatics. So Interdisciplinar Center for Bioinformatics and also the Institute for Computer Science, but at the Bioinformatics department. Then he moved for a year to Austria, to a chemistry department, Institute for Theoretical Chemistry. And then he has been in the Nazarbayev University in Kazakhstan for 1 year and something.
1 year and a half, 3 semesters.
Okay, as an assistant professor. So today the talk is about Boolean network dynamics. So thanks, Konstantin, and welcome.
Thank you. Thanks, Victor. Yeah, it's a great pleasure to be here again, like many times before. I was, well, often here as a visitor, and also have been employed here before 2001, 2002. So actually I've had this IFISC cap for a long time now. I'm allowed to wear it again.
It looks very unused.
Huh? It's actually, it was the one that's here. I have mine at home. I keep it safe. So, okay. Yeah. Sorry about my voice. Try to keep it okay. Bad week for choosing to have a cold. Good. Now to the topic. Yes, I will talk about Boolean networks. What that actually is. So it's a kind of coarse-grained way of describing the dynamics on mostly certain biological regulation networks, where we just have to simplify things as compared to writing down chemical master equation or whatever, to whatever detail you can go. So these are kind of on-off dynamics models, such that, yes, with these kinds of disordered systems, we can still say something, model specific biological systems. And yes, after an exposition of what people are doing or have done with this, I will go into an idea of how to efficiently analyze the dynamics on these, because you can imagine that it still can get quite involved to say specific things. In particular, for instance, does this dynamics, well, I haven't defined the dynamics, but suppose that we had a definition of what these nodes are doing, what the interactions actually mean. Then you want to know, is there a fixed, does the dynamics have a fixed point? It's already a difficult question to answer, and I will talk about an idea relating to this I'm working on right now. Good, but let's begin at the beginning, and let's go to the almost other end of scales, namely to what's actually happening locally. Biochemists might see what's happening locally. So if this could be an illustration of one of the nodes in such a large network here. And yeah, so it has two inputs, A and B. And this is the genetic string. This is the DNA here, and A and B can both bind to it. And when they do this at the same time, then they largely increase the probability that this molecule here, RNA polymerase, binds to it. And this again then starts the reading of this genetic code here. That's stored along this DNA molecule. And we'll turn that into an RNA molecule, which can then be translated into a protein elsewhere. Okay? So if we want to describe this whole process by an equation which already forgets about the stochasticity of these A and B binding here and just replaces that by the probability, which of course somehow depends on their concentrations of A and B. Yeah, then you have this kind of equation for the time evolution of the concentration of C, which would be the end product. I mean, so I told you the story from, well, this influence here and then reading this, and in the end there would be a protein. So you can say that this is the concentration of the protein, which is also degraded, and it's created by this process here with this binding probability, and of course there's a delay involved because all these things take some time. And yeah, okay, of course if now we wanted to go here and write this equation, if we have more inputs, of course something even more complicated, then with just two inputs for each of the nodes, then we would end up with something quite unmanageable. Okay? So that's the short rationale for saying, okay, maybe for certain biological processes, the actual fine-grained concentrations are not so important, but we are actually confronted with a set of coupled switches. So what's important is just to distinguish between a low and a high concentration. Okay, and this scenario here already suggests, okay, A and B have to be there at the same time in order to initiate this process here, which generates C. So in short, and with some justification also, if we analyze the shape of these things here a bit more, we can simply say, okay, whether C is there in the next time step is just given by an AND between A and B. If both of them have been there previously, then C is there now, and otherwise it's not there anymore because it's also degraded. Yeah, and then you are basically in the world of digital circuits. So rather than being on the empirical side, you could actually also go into synthetic biology and try to then build such logical circuits. So actually in this paper here, they also show that basically all kinds of usual gates and not so usual gates, like also exclusive OR, etc., can all build that with this biochemical material. And yes, so you could, for instance, build something like this, where you have two nodes that just map their input to itself, two times identity, and then this node in the middle just does a not AND operation. I'm just showing this here to already introduce what is called the state transition graph. Okay, so now you have a system of 3 nodes, and because each of them can be on or off, you have 2 to the power of 3, so 8 states. Okay, so the nodes in this graph here, call it graph now to make the distinction from network. I will call this network and this graph. So the nodes in this graph here are the states of this system, and the arrows indicate the transitions between them. That's why it's called state transition graph. Okay. Yes, so it's actually not connected because this node here is just a kind of bistable element that just keeps its own state forever and doesn't have any input. That's why up here you have everything when this node is 0 and here it's 1, and so you can, depending on what this node does, you can switch between this fixed point behavior, okay, here would be a fixed point, and this oscillating behavior. Good. Okay. Then for a long time, actually since the 60s, when these Boolean networks were kind of postulated or introduced, mostly by Kaufman, people have analyzed a lot just random networks, because actually you wouldn't really know in those times what the biology is doing there. There were not so many comprehensive measurements on what regulatory biological systems do. But then, at the beginning of this century, in the 2000s, then people actually were able to collect enough information, qualitative information on how nodes interact in order to come up with some, well, initially small networks. Okay, so here's a real starter on this business, which is the yeast cell cycle network. So for this standard baker's yeast, it just features the nodes that may be believed to be involved in the process of cell division. Okay? So in order for this species to divide, to survive, the cells have to divide when they've kind of eaten enough, when they're big enough, and this is the network that these authors here postulated to do the job. Okay, so there are several processes involved. For instance, you have to replicate the DNA. You have to kind of restrict the cell membrane, like here, and all these things you have to do in the right order. So okay, so it's really like a programmed, or it's a circuit that produces a certain number of steps. I'll show you in a second. And so what they simply did to come up with this, first collect the biological molecules that were believed to be involved in this process, and then just go through the literature and see what would be the kind of interaction between them. So CLN3, for instance, has a green arrow. That means excitation has an activating effect on MDF, etc. Okay, and this way you can come up with a coupling matrix Wij, where you just have plus ones and minus ones depending on whether that's activating or inhibiting, because you usually don't know the strength of the coupling anyway. Everything is qualitative. And then what each node does is, now we don't have general logical functions, we just have these kind of threshold functions. What each node does is just to make a weight, with this weight matrix, make a weighted sum of its input, check whether that's greater than 0, then it switches to 1. When it's below than 0, it's 0 in the next time step, and otherwise it does what it did before, 0. Okay. Good. So you could think, okay, that's throwing away most of the biological information there. It's probably also incomplete, or some of these measurements were actually wrong and so on. But the exciting thing there was that it actually does what the cell cycle does in yeast. And that is that if you excite the waiting cell, which is in this state, so this is now a state transition graph of this system, okay? So there's a waiting state here, and if you make a little excitation, that is, you flip one node, then you're actually here, and then it goes through this sequence of states, and if you analyze it, which we are not going to do now, then the sequence of ons and offs of these states here pretty much resembles what is happening there in biology. The time course that you can see, the biologists see when they measure what's happening when the cell divides. Just kind of looking at the cell in different stages and seeing which of the nodes are on and off. That's pretty much this trajectory here, okay? And what was also exciting is that there's kind of error resilience involved. So if I go to, I kind of make a perturbation of that system and go to some other node, then it will still, at least in this model here, find its way back to the standard scenario and end up in this fixed point. So that's the case for almost all initial conditions. Okay, so there are 1024 states because 2048 states because this has 11 nodes, so 2 to the power of 11. And almost every time you go here again. Okay. Okay, so this is the time course of the system here. Here you have the 11 nodes, and the whole trajectory here has 13 steps. And you always end up with this stationary G1 growth fixed point. So that's actually, in reality, in the biological system, the state where the cell does not divide but just eats, so to speak, in order to build up enough biomass to be able to divide again. And then once some other part of the biological machinery finds out that now there is actually enough biomass, then this start signal comes, and then this trajectory starts. Okay. Good. Now you can do a lot of things with this. You can, for instance, mutate this original network and see what happens if you delete or add some edges here. Right? So here this green one here, for instance, is not there. And then you see that you actually find a lot of networks that actually have the same trajectory. Okay, so this is called a functional mutant. So you can do many, can delete and add a lot of things, and this thing is still able to reproduce this. You can also make some deleterious mutations that actually have a devastating effect. So just destroy something in the network, just make a mutation in the yeast such that it can't grow anymore, and also these things are, which I don't show here, are reproduced by the model. Okay, so it seems that at least for the simple case of the yeast cell cycle, pretty much can be done at this relatively simple level of on and off states with the right couplings. Good, and now there are a number of studies. Every once in a while, some people make the effort, scan the literature for hundreds of interactions and compile a new Boolean network. And while initially these were relatively small, so we had this yeast cell cycle one with 11 nodes, now they have actually 100 and above nodes. Then, well, things are not so easy anymore, right? I mean, so here I can put basically the whole state transition graph, which in this case is actually just a tree. There's nothing cycling here. I can just put that on one piece of paper and actually see what's happening because we just had 11 nodes. And now with these node numbers, that's completely hopeless. So, and in fact, it's already, so we were talking about these fixed points, for instance. That would be the first thing to look at in the yeast system, is at least this fixed point, is that the right thing? Now you go to a more complicated system, say this also has an important fixed point, and maybe it's not exactly in the model, not exactly the same as in the real system, but we want to at least answer the question, does this Boolean system that I just compiled, does this have a fixed point at all? Okay. Before you start to ask more complicated questions. And yes, computational theory computational complexity tells you that this is already a quite difficult problem. I will not go into this, but not all the details here, but the thing is, okay, you take the Boolean mapping, which is basically our Boolean network that maps states to states in the next time step, is basically an iterated map on these Boolean state vectors. And then this problem, does it have a fixed point? That's NP complete for those who know the theory. So it just means we don't have a polynomial time algorithm in general, polynomial in n. So we don't have any efficient algorithm to decide this. Okay? It's a bit similar to, for instance, the difficulty of finding the ground state of a spin glass, or to finding certain cycles in networks. So all these things, we don't have a fast algorithm. Good, and this is where the work in progress starts. And I just took this this warning here as a first souvenir from Kazakhstan. And it's actually not the full thing, but this is what I had at the construction site in front of my house. So that's also a kind of warning complete thing with all the disclaimers that you can think of, and one actually telling you to go straight and the other to go around here. And actually behind this is just a trivial sand pile with some snow on top. So it wasn't actually that dangerous. Okay. The things I want to do here are also not so dangerous, so they're actually, I hope, quite intuitive to grasp. Okay, so we want to analyze the dynamics of on these relatively large interaction networks in particular. Be modest first and just try to find fixed points. Then what I develop can actually also find other attractors, but think of fixed points most of the time here now. And okay, wouldn't it be nice if we could just kind of distribute the work by cutting the network apart, and then the student does one thing and I do the other thing, finding the fixed points, and then we put the results together somehow, right? So let's maybe not cut it in the middle, but cut it maybe such that we interrupt as few interactions as possible. But still, then, yeah, it would be nice, but what does it actually mean that we just consider a sub-network here? What's the dynamics on the what's the dynamics on the sub-network? Nobody has told me this. I mean, I interrupt some connections, and should I then, on this subnetwork that I'm considering, the connections that are coming from the rest, should I just say, okay, these nodes on the other side of the cut, they're always zero, or what is actually the most useful thing to do in the end? Of course, the definition has to be suitable for my goal. Okay? Good, so here's a definition of what I actually want to do now, is to define a meaningful restriction of this Boolean dynamics to a subset of the nodes. And then this hopefully will have two benefits. First of all, I can just be satisfied with this. Maybe I just take the core of the network and say, okay, in principle, things happen here. And I can already say a lot of things of what's happening in the core of the network and just forget about the periphery. Or I can, if the definition does that, well, I can divide the network up, as I pointed out before, and analyze on these subnetworks, and then hopefully put things together in the end and still say something reasonable. Good. Okay, this is a project I started with students there at Bias University, Andrei Sakryukin. Good. So here, just to remind you one more time, okay, we have the Boolean network, we have its state transition graph, and attractors are those subsets of nodes from which the dynamics doesn't escape. Okay, so here from this node there's no outgoing arrow. So that's actually also a fixed point, but in general an attractor. And this is an attractor of size 4 in this case. And so they're actually minimal sets of states from which the dynamics cannot escape. From the whole set of 8 states, the dynamics can't escape either, but the whole state is not an attractor. Good. And we are mostly looking for these fixed points. Just to stress that one more time. Good. And now, yes, I pose the problem. Suppose in my example network here, I want to make this split. So I want to split it into the subnetwork containing these 2 nodes, and the rest is another subnetwork. Okay, for this X3 it's actually easy because I don't cut any incoming connections, so that will reasonably just stay the same. But here I cut this connection into the NAND node into X2, so I don't really know what to do, such that things might make sense in the end. And okay, the definition that I use now, which in the meantime now sounds natural to me and hopefully then also to you, will become clear why I do it like this. The definition that I use now is, okay, I have cut these connections to nodes outside of the network, rest of the network I'm considering now. So here in particular the blue node is missing now, so I don't know what it's doing. And so I kind of project that out in the sense that I keep only, working on the state transition graph, I keep only those state transitions that happen regardless of the state of those nodes that are gone, that I don't know anyway. Okay. So what does that mean here? Okay, so suppose I don't know this blue node here, I don't know whether it's 0 or 1. That doesn't really matter for this state transition, because whether the blue node is 0 or 1, it's this state transition here, the green node flipping is there anyway. Okay, so I keep that. Likewise, this one is also here, also doesn't depend on the blue node, whether it's 0 or 1. Likewise here, but this one is not there. Okay, if the blue one is 0, then it wouldn't happen. So for this state transition, I really have to know what the blue node does, and so I just leave it out here. Okay. So it's kind of the picture is kind of trying to say something about causality, so to speak. So here it's really the blue node that causes this flip, but if I don't know whether it's there or not, I just leave it out. Okay. In the end, this will just help me to find the fixed points. Okay, and then I can actually, it's not so important now, I can actually analyze what I have here now, and then suddenly this red node, instead of getting the input from the blue node, it has a self connection here if I want to write it down as a Boolean function. Now extract it back from the state transition. Good. So this would be the dynamics of this subnetwork. Okay. Now, yes, one could prove something about the state transition graphs and why these things work, but I will just tell you first what I do, and then afterwards by the examples hopefully it gets clear why this works. Good. So I partition the network into suitable subnetworks. Then somehow I find the attractors on the subnetworks. Either they're already small enough, or I have to partition them again. Then that's why the algorithm might get recursive. And then when I found them on the smaller networks, so all the attractors that I find on the smaller networks, they are now sets of states, right? And now now I find candidates for the attractors of the whole network just by considering all set products of all attractors on one part and on the other part. So I found an attractor here on nodes 1, 2, 3, and I found an attractor there on nodes 4, 5, 6, and now I just make the set product of these, and I do that for all the combinations. Okay. So to feel a little bit more at home, I do this now for the Ising model rather than any strange Boolean network. Because in principle the Ising model is also just a Boolean system when I consider it at 0 temperature and with asynchronous update. So what you would maybe call the 0 temperature Markov chain for the usual Ising model is also just Boolean dynamics, right? For each site, for each node, I know exactly when it's allowed to flip depending on the neighbor's states. Okay. Okay. And when is that the case? Well, when it doesn't increase the energy, and here on the square lattice, that just means it feels happy and doesn't flip when at least 3 of its neighbors have the same state. Or kind of the contraposition to this, if a node has at least two states in two neighbors in opposite states, then it can flip. Okay, and as long as at least one node can flip, we are not on a fixed point. Remember that we're still trying to find these fixed points on a given system.
You said you're using a synchronous update?
Asynchronous, yeah.
Random or sequential?
Any. So I'm on a fixed point when when all nodes are happy, right? When none of the nodes can flip anymore without increasing the energy. Good. What are the fixed points of this? What are the fixed points of this system? Well, there are these stripe patterns. Either I have the totally ordered solutions anyway, or if there is disorder remaining, then I have these stripe patterns where now none of the nodes can flip anymore because each has at most one neighbor in the opposite state. Okay? Good. And now I can see if my strategy works, at least for this one here. So, okay, I go to subsystems and I start with one spin. Okay, so one spin isolated doesn't know any of what its neighbors are. I've cut all the inputs, and so it can't flip. It doesn't know anything. So that's definitely a fixed point of this subsystem. It could only flip if it saw definitely at least 2 of my neighbors are in the opposite state. Well, but it doesn't know that because it doesn't know any of its neighbors. So these 2 are the fixed points of the one spin subsystem. Then, I said I make these Cartesian products. So now to go to 2 spins, put 2 one-spin systems together and make all pairs of these here. Okay, so these are all 4 pairs. And again, I can't exclude any of these possibilities. They're actually all fixed points in these systems because none of them sees enough neighbors with the opposite spin in order to flip. So also these are. Okay, now I take again 2 identical systems with 2 spins and generate a 4-spin system. So I generate all 16 4 times 4 pairs of these here as the candidate fixed points. So these are now the 16 combinations. And now the thing starts to become useful because now I actually have 3 known neighbors, and when at least 2 out of them have the opposite spin, then I know I can flip without increasing the energy. So
Why 3 neighbors? Why 3 neighbors?
I have 3. I mean, here I have 3 known neighbors in this system. Each of these spin has now 3 of its neighbors actually included in the subsystem that I consider.
You want
Ah,
to
it's true,
central
sorry. Yes, completely wrong. Okay. Delete that from the recording. I'm sorry. Yes. Yeah. So you have 2, but that's enough to. When both of them are in the opposite state, then I can flip. Okay. Then I know for sure that I can change state without decreasing the energy if I have at least 2 neighbors in the opposite state. And so all these kind of corner configurations here, where I have 1 against 3, they're off. They cannot be fixed ones. You know, they can in no larger system, then also this subconfiguration can occur when I know I'm on a fixed point. Okay. I think I used to do it in the beginning by giving the wrong number. So I have 2 neighbors here, and when both of them have the opposite state from myself, then I know already I can change state without increasing the energy. No? Because when I satisfy at least these 2 bonds, and it doesn't matter what the other 2 bonds were. I mean, in the worst case, yes. In the worst case, these were the same as me. Then I just stay level with the energy. Otherwise, I even go down. Okay, good. So all these are gone, and so I have reduced the number of candidates from 16 to 6 here, and now would repeat the process to go to an 8-spin system. Again, put all pairs, so 6 times 6 pairs together. Then again, see which can be excluded as fixed points, and so on and so forth. Good. We could also go through the example with my 3-node network, but I think I'll just skip that now.
How did you go to the next level?
What?
I was missing how I was asking how did you go to the next level?
Yes. Okay. So
I mean, there are many ways you can do it, right?
I put.
No, you can delete the others. So go to the next one.
Yes. Okay. Yes. So.
And then how do you?
Yeah. So now I take. Well, okay. My 8-node system is obtained by putting next to each other.
Yeah, we have at least 4 ways to put it together, right? Not just 6 by 6.
Yeah, that's rotational symmetry. So.
No.
Yes.
I don't think so. Yes.
No. What?
No, you can take the one on the lower corner,
Yes.
left lower corner.
Yes.
And you can put it next to the top one. There are at least 2 positions in which you can put this.
Ah. Okay. But I.
Who normally do that?
But I always do it the same way. So I mean, I just have to. I have to break the symmetry once, so to speak, but it doesn't. I mean, okay. Now I have these two spin systems, and I put them, one above the other. It's always.
Above the other.
Yeah. I mean, okay. It's really just a matter of how we put things over in the.
Put it on the right. You put it on the right or left.
Yeah, but these. I mean, you have the symmetry here. I mean,
Well, in this example,
if you.
in this particular example, I don't see the same to put it on top or to put it on right.
Okay, what would be, if you say particular example, what is the
Okay,
general?
No, in this example, I think it's the same.
Yeah, because it's easy model on a square legs, yes. I mean, of course, yes, when I go back to my Boolean networks, but then it's given by the original network from which I have taken the subnetworks, how I have to put them together again.
I think, sorry, you only take 2 rows. You don't take 4 subsets.
Well, at least 2.
But I mean, you take 2, and then every time you take 2 of these subsets to make one bigger. So you go to 8 spins, not 16. And
No, that's all enough. But you can put them one on top of the other, and continue with your figure. You put one to the right of the other.
But
Yes, so that's the same because they have this rotational symmetry also in the solution.
Yeah, once with this rotational symmetry is kept all over for many steps.
Yes, I think you can prove that.
Now listen, the next step, you have 4 by 8. You can continue it 4 by 16 or 8 by 8.
Well, it's given by what we are originally doing here because we are looking for a fixed point. So if I rotate my spin systems by 90 degrees, then I still have a fixed point if I were on a fixed point. Because it's only counting how many neighbors I have in opposite states. And so it doesn't depend on my orientation. If I rotate, I still have.
We need to draw that on detail. No example. How can we do that later?
We can write it down and prove together. Or you give a counter example, which is still good. Good. Yes, we could also do that for the 3-node example, but I think I'll just skip that now, not to go too long. And yeah, so as I said, it's work in progress, but we made some first tests here, and the first simple thing we looked at were some elementary cellular automata. So that's just a one-dimensional, it's kind of a particular Boolean network in the sense that you have just a ring of nodes. Each node gets input from itself and from its two neighbors on this ring, and all nodes have the same rule. That's basically how you can capture cellular automata as Boolean networks. And there, at least for some of these rules, the nice thing was at the time that you take the number of iterations in the algorithm that you take in order to find all the attractors, not just fixed points but general attractors now, that's actually proportional to the number of attractor states that you have. Okay, so the time to find something scales proportional to how much there is. So that's
due to the simplicity of your considered network configuration. No?
Yeah, you cannot prove anything general here for these cellular automata, but at least there it works.
Those are ring ones, you say.
Mm-hmm. Good, so this was the first test. And then what we did was to get back to actually this network here. We kind of cut it apart. Actually what we did was to just grow it node by node in a more or less random fashion. This as a first test. And what seemed difficult in the end was then not so hard anymore. So that worked quite okay. So actually we have here in principle 2 to the power of 17 different situations, because this thing also has, going back and forth here, because this thing also has 17 fixed inputs where you can kind of encode the environmental conditions. In principle, we have to do the whole thing 130,000 times for all these combinations of environmental conditions here, but each search for each of them took us only about a second of computer time, and so the whole thing took about 30 hours to really get the complete fixed point information on this. And unfortunately this is where it ends, because we should look at the fixed points and maybe compare that to the biological meaning, but that's why it's work in progress. But at least, yes, we get the full fixed point information. We also find that actually for most of the environmental conditions, maybe around 94%, you don't have fixed points at all. For some of them you have a lot of fixed points, so for some environmental conditions the behavior is kind of stable-ish or fixed point-ish, but often the system doesn't find a fixed point, it just keeps cycling around. Good. So yes, this is where it ends. I have shown you what Boolean networks are useful for simplifying and sometimes understanding biological dynamics, making some predictions, and then I've gone into an algorithm for analyzing the dynamics of larger networks, which is even though already simplified by going to this 0-1 dynamics, which is still challenging. And yes, the definition of what the dynamics, what this discrete dynamics should be when you restrict it to subsystems, maybe that's also of use somewhere else. I've shown you here with the easing model, you can apply it there. That was just to check the ideas, but of course one could also say, okay, I take now a spin glass and just cut it apart and try to find all the method-stable states of the spin glass, or fitness landscapes. I also have this kind of asynchronous update dynamics, adaptive walks on evolutionary dynamics on the fitness landscape in terms of adaptive walks. So yes, I'll follow this and maybe some of you also have an idea where I can apply these things. Thanks a lot.
We have some time for questions or comments.
You started actually with the dynamical equation, which included the characteristic timescales and delays and all these things. Your fibroblast network, does that include, for example, delayed interactions?
No, there's well, you have a clock, so to speak. So because there is a delay, because there's some time goes from between.
So in that case, you don't use asynchronous updates, so you do have a clock in your system. And so how far does it then represent the dynamical system that you want to model?
Well, for this one you can do you can actually do both. No? I mean, the authors mainly write down the Boolean functions and then they analyze something. Some things are actually independent of what kind of update you use. For instance, the fixed points.
But the solutions will be different.
No, the fixed points, for instance, are the same.
Fixed points are the same.
Yes, and yeah, so you can run it. I mean, the second part here, the algorithm that works on state transition graphs that come from asynchronous update, and then this one has been used with both. Of course, some authors do this. Some authors put a lot of noise on it. And some authors do the deterministic synchronous update. So it's not really clear what to use. I mean, depending on what you can do and maybe what you're interested in, you sometimes do one thing and sometimes the other. So the whole role of time scale and noise and so on, there's no common ground yet in this business.
More questions?
I wanted to make a very general remark that in your talk you stressed the search of fixed points of the network. I just wanted to comment in a very general way that in many biological systems, they are not the fixed points that are interesting, but they are more the transient states. I mean, there are systems that are, I mean, you could think as information processing systems. So you have a system that has some stimuli, and as a response to that stimuli, I mean, something happens, and so on and so on. And I may be interested, I mean, which is the time scale in which the system reacts to this external stimuli, or, I mean, this is a general remark.
Yes, so yeah,
transient states are important sometimes more than fixed points.
Yeah. So this is exactly what you find here. So it's exactly the transient into the fixed point that is what we're interested in here, because that represents this process of cell division. So there's exactly as you say, there's a trigger, and then which in this case is the cell size signal. So I've grown big enough, I can divide, and then then this cascade here starts. Yes. So that gets even more complicated. So I think from the algorithmic side, I wouldn't even know how to start. I mean, by saying, okay, I now want to find directly the transients, because then I would already ask, okay, into what? rare. So I think it's, yes, I mean, so often these are the more important things, but for finding them, I think we have to start with where the transients go, and these are the fixed points or in general the abstractions.
Or do experiments.
You have an algorithm to find fixed points. Now, can you say something general, how good or bad is the algorithm depending on the topology of the network?
Not yet, I think. Of course, when things are
Because
sparse,
the algorithm, the efficiency of the algorithm will depend on the topology in some way, right?
yeah. So when things are sparse, then it's usually easier. Although, for instance, this example network here that I use is not so sparse. It's actually denser than some other that I used, and I used that other one first. So it's actually this one here about the gamma secretase, which also has more nodes. And this one is really sparse, and there we don't get it yet with the simplest approach. And we just run out of memory, or it just takes too long time. And that's because the Boolean functions here are kind of different. So they are already very fixed pointish, so to speak, in the sense that they most of the time keep their own states, and they have lots of self-couplings. And so yes, it's hard to say something up front how difficult it is for different networks. It really depends on the network and the type of Boolean functions that you have.
If I understood it correctly, what you do in order to find the fixed points, you take the network motives, right? And you grow them and see which network motives are stable. Is it always clear that this gives you the right answers?
Yes, that you can prove. So yes, so the algorithm is correct. Yes.
It might not be efficient always, but
Yeah, exactly. So it can, things can. I mean, the things I have to, even though maybe I don't have any fixed points at all, in the end, during the runtime of the algorithm, just I run out of memory. I mean, gigabytes of memory, and just to store temporary solutions where only at the very end I find out okay, they are actually, I can throw them
Because just
away.
considering the number of possible connections and logic operations, this must blow you around your ears. This must completely explode. I mean, in the case of the spin class, it's kind of a trivial case that you show. I mean, because there the network configuration, the network motives are trivial. But
The easing model, the spin class in general is also
yes, the easy.
Yeah, of course, that was just for illustration. Yes, so if you don't have any frustrations, it's super simple. Yes.
So what do you do? You are raising toy in a triangular network.
I haven't tried, but I think I can.
Yeah, anti-ferromagnet in a triangular network. But that's the simplest case of frustration.
I'll tell you next week then.
Okay. Good answer.
Some of those Boolean networks can be understood as a simplification of some differential equation model. Now you have an algorithm to find the fixed points of the Boolean system. Is this going to do something about the system of differential equation from which this Boolean network can come? For example, for systems of two differential equations, finding the number of fixed points is an unsolved problem. There is no theorem for that, for example. Only two. It's possible that you can approximate some kinds of differential equations by Boolean networks and then tell something about the original system. Have you thought what is the relationship between fixed points in the Boolean approximation in some continuous system.
Yeah, I mean, of course, if the discretization has been done with care and reason, then there should be a connection. But the question, I mean, there's no unique way of going from a system of differential equations to this Boolean setting. I mean, sometimes you actually you want to have at least 3 different levels, right? This is the mildest complication that you can have. So actually, in some of these Boolean network studies, they then they either say, okay, here's an exception, here's a ternary node that actually where we have to take into account that this intermediate level is very important, or they split it into 2 nodes, which is also kind of strange. So there's already no unique way of discretizing. So, and of course, you throw away a lot of information on it, so you can just hope that at least the fixed points that your Boolean system has will also be found in the differential equation, but of course there could be more, because you throw away levels, and that's also not clear how you actually discretize. And mostly it's not done, because mostly what people what people do is not to first write down the differential equations and then discretize, because then you could at least on the way somehow check back whether things run similarly, whether the dynamics has some resemblance. But they really just scan the literature for qualitative statements on what upregulates what, so to speak, or downregulates. So what is somehow found to be postulated to be connected with what else. And so you don't actually, for these systems, you don't have the
More fundamental.
Coming back to the easy model you showed us, imagine that you are attacking the iteration, and then would it be interesting to consider different sizes for the subnetworks?
I mean, if I should kind of split the lattice into parts that are of different sizes.
Yeah.
And here, because there's no disorder, probably not. I don't think it could be any advantage. But of course, if if you have frustration here, so if there are some antiferromagnetic ones, this is the Maxi's example, or it should actually be disordered, so you shouldn't have a translational symmetry. Then, of course, what you can do, you certainly start with a one spin system, and now you have to decide which cluster you merge with which other. No? And then you can apply all kinds of heuristics. The simplest one would be, okay, I take the next merge as that consumes the smallest memory size, where I have to remember least, where I can exclude most candidates. So this is actually part of it we are already doing in these algorithms on the real networks. So you actually kind of greedily try to optimize things on the way by choosing to merge clusters in a way such that you can get rid of most of candidate solutions. Yes, and then you will have different cluster sizes on the way.
Well, if there are no more questions, let's thank Konstantin again.